The methods that we've looked at so far for solving ordinary differential equations have all considered advancing our solution from time is equal to ti to time is equal to ti plus 1. Multi-step methods are a little bit different. So the methods that we've looked at so far are Euler's methods, second order Runge-Kutta methods, Hoynes and the midpoint method, fourth order Runge-Kutta methods, I'll call that RK4, and our adaptive RK4, using Richardson extrapolation to make it fifth order. So all of these have increasing accuracy. The question arises, of course, that isn't that enough? Haven't we done enough? Well, the answer, of course, is no. There are other methods that are interesting to investigate. So let's have a look at an analytic integration of our ordinary differential equation. So the basic idea behind finding the analytic solution of a first order ODE, and we're going to write our ODE as dy dt is equal to some function in t and y. So the basic idea is we take that ODE and we expand these differentials to write dy is equal to f of ty dt. We can then integrate this expression to give us the integral of dy is equal to the integral of f dt. And finally, the left-hand side integral is equal to y, and the right-hand side integral is something that obviously depends on f. So that's the basic idea of what we're doing when we integrate our ODEs. So, as I mentioned at the beginning, all methods to date use limits of ti and ti plus 1. So, if we put those limits into our integral down here, we end up with the integral of the integral dy from yi to yi plus 1 is equal to the integral of f from ti to ti plus 1. The left-hand side integral is obviously integrated directly, and that just gives us the limits of yi plus 1 minus yi, and we shift the yi to the right-hand side to give us that yi plus 1 is equal to yi plus an integral of f integrated from ti to ti plus 1. Euler, midpoint, RK4, etc. are just different ways of estimating that integral on the right-hand side. Multi-step methods take a different approach. Instead of starting with the value of the function at ti, in other words that's yi, and integrating forward to ti plus 1 to get yi plus 1, why not use information from earlier steps to improve our estimates? So for example, we could use values at yi minus 1, yi minus 2, etc. That's going to give us extra information. It might give us extra accuracy. Now, because we have more information, if we're going to use more points, we need to choose different limits of integration. So let's write our integral as an integral from ti minus n to ti plus 1, and therefore our integral dy needs to go from yi minus n to yi plus 1. Obviously, again, the left-hand side integrates just to y, evaluated at the two endpoints, and we move yi minus 1 to the right-hand side, and we can show that for a multi-step method, yi plus 1 is equal to yi minus n, where n is just some number we haven't yet chosen, plus the integral from ti minus n to ti plus 1 of f dt. So we're doing a different approach here. We're going to illustrate this by way of example, and we're going to look at an improvement to Hoynes' method. So let's just briefly review Hoynes' method. In a predictor step, we calculate a new estimate using Euler's method, so yi plus 1, and we use a superscript of 0, saying it's our first, well, it's our 0th guess if you like, is equal to yi plus h times the function value at ti yi. That's the predictor. It's Euler's method. The error scales like h squared. The corrector step then is yi plus 1 m, where m is either our first or our second or our third iteration, and that's equal to yi plus h on 2 times the function evaluated at the initial point plus the function evaluated at an estimate of our end point. And for the first guess, we put yi plus 1 in there. Now, when we looked at Hoynes' method previously, we didn't iterate on this step. We only put yi plus 1, 0 in there and called it quits. However, we can iterate the corrector step multiple times if we wish. Turns out that this right-hand side, or this part of the right-hand side here, is equivalent to using the trapezoidal rule to undertake the integration. It's an h on 2 multiplied by function value at the beginning plus a function value at the end. The trapezoidal rule has an error that scales like order h cubed. I've already mentioned that m indicates the option of iterating on the corrector if we want to. We don't have to, but we can. However, there's an inconsistency in the order of the predictor and corrector. So the predictor has an error that scales like h squared, and the corrector has an error that scales like h cubed. Ideally, we would like to make both of them the same, which would mean that we would really want to make the predictor order h cubed as well. So that's what we're going to have a look at doing. So let's look at our multi-step formula that we derived previously. yi plus 1 is equal to yi minus n plus this integral. And let's set n is equal to 1 in here. So that just gets us to write yi plus 1 is equal to yi minus 1 plus the integral from ti minus 1 to ti plus 1 of f dt. So the question is, how can we approximate this integral here to give an error that's order h cubed? And not only give us an error that's order h cubed, we have to be able to use information that we've already got, because it's the predictor step. So this is what we've got. Ti minus 1, we know ti. We're trying to find the value at ti plus 1. We're trying to make a predictor of it. We know this function value, we know this function value, but we don't know that function value. Well, let's have a go at using one of the Newton-Cotes open formula. We did these a number of lectures back. If we use the simplest formula we can see that the integral is approximated by this rectangle that passes through the central point. It doesn't use either of the endpoints of the interval. It turns out that this integral here is equal to twice hf times the function, twice h times the function value at the midpoint, and the error in this is order h cubed. So we now replace our predictor, our regular Hoynes predictor, by this new predictor. We say yi plus 1, 0 is equal to yi minus 1 plus twice h times the function evaluated at the point ti yi. That's our new predictor step. So this uses the Newton-Cotes open integration formula, and it has an error that scales like h cubed. So we've now got a predictor that has the same order of accuracy. The corrector doesn't change. We still use the same corrector. This uses the trapezoidal rule, which is a Newton-Cotes closed formula, and has an error that scales like h cubed as well. Why do we call this the non-self-starting Hoynes method? Well, when I is equal to 1, the very first step, we don't yet have a y0. We don't know what this thing is, so we can't actually use this predictor step at the very first step. So we need to do something special at the very first time step. So we might need to use the midpoint method or the normal Hoynes method or something else. But apart from that very first step, we can go. Based on the Newton-Cotes open integration formula, predictor, which is given by that step there, we can show that the predictor error is equal to this, 1/3 h cubed f double dashed evaluated at some point psi p. Again, we don't know where psi p is in the interval and we don't really care. But the predictor error is equal to this. Therefore, we can write the exact solution is equal to our predictor estimate plus the error term. Okay, this is approximate because there will be higher order terms here. Now, based on the trapezoidal rule corrector step, given by this thing here, the corrector error can be shown to be something a little bit similar, except now it's equal to -1/12 h cubed times the second derivative evaluated at some other point, psi c, in the interval. Again, we don't really care where psi c is. So we have an estimate for the predictor error and an estimate for the corrector error. If we use the corrector step, we can write that the exact solution is equal to our corrector minus 1/12 h cubed f double dashed at xi. Now, assuming that our second derivative varies slowly, in other words, this and this are pretty much the same, we can subtract this to write yi plus 1, 0, that's our predictor, minus yi plus 1, nth guess, that's our corrector, is equal to minus 5/12 h cubed f double dashed at some value of psi, which is inside the interval. Now, that's what we just wrote at the bottom down there. We know that the corrector error is equal to minus 1/12 h cubed f double dashed. Therefore, using this expression here and dividing it by 5, we can write that the corrector error is equal to 1/5 yi plus 1, 0 minus yi plus 1m. So in other words, the error in the corrector is 1/5 the difference between the predictor and the corrector. The first point about this is we can use adaptive step size control to keep this error, EC, below some kind of specified tolerance. So we have an estimate for the error, we can see whether it's acceptable or not. We're not going to consider how to do this here, and it is not examinable. We can also use our error estimate here to adjust our corrector. So, from the fact that the y exact is equal to our corrector minus 1/12 the error estimate, we can just replace that by equation 1, which gives us y plus 1 exact is equal to yi plus 1 m plus yi plus 1 0 minus yi plus 1 m and 5. We just group the like terms and we come up with a better estimate is 4/5 of our corrector step plus 1/5 of our predictor step. That is the non-self-starting Hoynes method, which has been improved.